Hey, hi there. Welcome to my report on OCR, A Physics A-Level paper 2017. Sorry about my appearance. It's hot right now. I don't have any other excuse. Okay. Right. So, OCR's paper, there was not very much particle and medical physics, which was a surprise. And maybe what I hope happens in the real thing. No, actually, it's quite good because it's quite a prescriptive topic. Like, once you have all the knowledge and you understand the system, it's quite good. And also, I suppose it is interesting real life processes. Anyway, my first big error: know your SI units. Which ones actually are SI units? I thought charge was an SI unit. It really isn't, and I've written like a psychopath all over my paper that charge is not an SI unit. Current is. So take a look at them. I think from the mark scheme, the accepted ones are for temperature and so Kelvin, not degrees, Kelvin, mass for amount of a substance. They gave some in the question, so not all of them were valid answers, but yeah, have a look at those. The first long answer question, question 18, was pretty nice. Yeah, I don't think there was that much that could be said about it other than, you know, the obvious things. So draw that curve of best fit. Show what mistakes are. Obviously, there was a big missing data point. The readings were not taken in equal increments, so you can't say that it shows an not an accurate trend, but you know, it's a point of note. Yeah, suggest improvements. That you need to use an ammeter and a voltmeter. P is IV to take the readings. Yeah. To question 19. It's the kind of thing that's very easy to know exactly what you're talking about, completely understand the system, and then not get the right answer because of the wording. Basically, you always need to refer to the fact that intensity is just a rate of incident photons per area. You know, I keep slipping and saying, oh, it's the amount of photons per area, which doesn't affect. No, just say it's the rate of photons, and referencing the threshold frequency or work function, or preferably both, rather than, what did I say? Defined, okay, light is a distinct quanta of energy, a photon is a distinct quanta of light that is defined, that's energy is defined by its frequency, and so energy transferred, blah 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 blah. Yeah, it just doesn't spell that out quite clearly enough, and it is also easier to say if you have those words in your head that you need to hit saying because of the threshold frequency, where intensity does not define this, where intensity is independent of the energy of each distinct quanta of light. Yeah. Blah, 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 blah. I strongly misread 19C, so that's just your daily reminder to read the flipping question and drink some water. Definition of electric potential. Prescribe it, memorize it. Unit positive charge from infinity to that point. Obviously, because it's the amount of work that you need to do to push it towards a positive charge, because we always assume positive in physics. Our unit charges are positive. So whenever we do arrows, that's why we do it in the direction of a positive qualifying object, i.e. mass for gravity or charge in electricity would travel. From infinity to that point, obviously it's going to be repulsive, so that's why work needs to be done. And that's where we get electric potential. Oh, question 22bi. I did get it correct, but I think you can more clearly and in fewer words than I did say rate of change of flux linkage, because I left it right to the very end to use that terminology, which might not be the wisest thing to do in an exam. Because obviously I know what I'm talking about, but if someone who's, you know, got 500 of these questions to mark, going to read a giant paragraph and wait for the correct word at the end. Maybe they will, but you know, for safety, you should probably trust that they won't. Our parameters for strong nuclear force: 0 to 0.5 femtometers repulsive, 0.5 to 3 attractive, and strongly attractive, and so can overcome the electrostatic repulsion between protons in a nucleus. And it is a short range force. That is a phrase that we want, and it's I think highlighted, might even be in bold in the mark scheme. It's a short range force, which obviously you can say, oh, but it says that by saying the range and distance, but it's better to just use those words. Why you need high temperature and pressure for fusion, i.e. in a star or a fusion reactor. You can explain it a lot, but I think the easiest thing to say, and the easiest thing that will get you marks in the exam, because unfortunately that's what we're working for right now, is each particle needs to have high kinetic energy, so that it's moving at high speed, high velocity, so that it is close to other adjacent nuclei. Is it nuclei here? We'll just say particles. Might question context dependent. To overcome the electrostatic repulsion between protons, basically, and then they need to be high pressure so that they are already at that closeness. It's all about them being close together. So you could say things like what I said, the higher likelihood of collisions when things are moving faster, but I think closer is kind of what they're going for, because both are true. But yeah, it's a more physics answer to say that they're closer. Question 24. See, I just made a calculation error. That's silly. I just wrote the wrong power of 10, so don't do that. Oh yes, the process of PET scans. Be careful before you get too bogged down in saying the function of the collimator and the scintillator and the photon multiplier. Make sure you've already said the way that it's detected, because sometimes questions want all of that, but sometimes it just wants the method it's detected. So positrons are emitted, they annihilate with electrons in the body, and then conservation of energy and momentum. 2 gamma photons have to be emitted in opposite directions to each other, and then opposite, highlighted in mark scheme, in opposite directions to each other, and then you can detect them coming out of the body, and then the difference in time they are detected, you can use to detect the position from which they are emitted in the body, which shows the accumulation of, in this case, fluorine 18, accumulated from the radiopharmaceutical, and where the radiopharmaceuticals accumulate, they accumulate in areas of high metabolism, because they're usually attached to things like glucose, which can be good for detecting a tumor, for example, because they have a very high metabolic rate. But if you take biology like I do, don't accidentally start talking about cancer biology, because that's not what they want. Everything else was more or less okay. Multiple choice questions. Remember, intensity is proportional to amplitude squared. Intensity is proportional to amplitude squared, because what is amplitude? It's basically an energy. What is intensity? Energy per unit area, which is squared. Okay. Remembering, even though it's given in the formula book, they lied. N2 does not equal 1 over sine c for the critical angle of a barrier. N2 is equal to N1 over sine c. So remember that. Question 6, what, draw it. I always say just draw it. What kind of shape, I guess, of interference pattern you can have in each system. So if it's a tube that's closed at one end and open another, the pattern has to look like this: closed, open, and then you can add a loop in the middle, but it still has to be closed at one end. So by that you can work out the different wavelengths that can form a standing wave in that system, and for question 6, the different frequencies. Yeah, I think that's all I have to say. Quite a nice paper. I got 82%, I think, which isn't amazing, but it was still an A-star, I think, for this paper. So really hope the real one isn't like this and nothing like paper 1, which I'm sure everyone else agrees with. Okay, good luck everyone. Bye bye.